My name is Joel. I've been working for the past several months on with Cadena on this property checking system for their smart contract language Pact. So I'll be going through the work that we've done and showing some examples of what you can do with it and how it's implemented, and some other languages which have similar features. So I'll start with a kind of short introduction to Pact. I'll try to get through kind of the basics of the language quickly, and try to not cover a lot of the language, but just get through some of the basics so that we can show some code examples. So it's an intentionally simple language, which is not Turing-complete. There's also no recursion and no loops, which is related. And the data model, so it's a smart contract language, but the data model for this smart contract language is a little bit different from what you might expect in Ethereum or in Bitcoin. But it's kind of like a SQL-like table model, which we'll show examples of in a minute. And it has a simple authorization primitive called key sets, which you can think of as a set of public keys or the set of users authorized to take some action. And I'll also show examples of that. And it has a transactional semantics where a transaction will abort, and nothing in that transaction will then be committed to the ledger if transactions can abort without committing anything to the ledger. And we'll show that as well. So the data model. So here we've defined a schema, which you can think of as a record, which has a balance, which is an integer, and a key set, which is more or less a set of users who can do some action. And we define a table, accounts, which is a set of account. And visually, Alice and Bob have 10 and 5 respectively. So here's our first function in Pact. This is a simple transfer function where we're just transferring some amount from an account to another account. So on the first line with the let, we read from the from account the balance, and then we read from the to account the balance. And then we write the updated balance to the from account and write the updated balance to the to account. Also, feel free to stop me if there are any questions at any time.
What are the strings doing?
So the string on the second line? Yeah, the string on the second line is just a doc string.
Okay. Accounts is a global variable?
Yes. So accounts would be, accounts is defined here. So I'm kind of borrowing the scope from this slide. And we can also add optional types. Otherwise, they would be inferred. So for an example of authorization, we can add 2 more lines where we read the key set from the from account, or in other words, the set of users authorized to update that account. And then we enforce that the current context has that authorization.
You don't see the context in this code, right?
No.
Right. It's implicit.
Yes. And one more enforcement, we can enforce an invariant. We don't want to transfer this money if the from account doesn't have enough. So for a little bit of motivation on why a property checker is useful, there have been a lot of bugs in smart contracts in the past year or two. There have been high-profile ones like the DAO attack, the parity multi-sig wallet bug, and batch overflow. So I think security is really holding us back from building complex, non-trivial apps. If you need every line, it feels like kind of the largest smart contracts we can scale to are on the order of 100 lines or 500 lines with the current technologies that we have today. And unit tests are not sufficient against adversaries. So for some examples of inspiration for the Pact property checker, I'm going to give 4 or 5 examples of other languages that have similar features. So one is Daphne, which I think comes from Microsoft, where you see requires and ensures and invariants. So we'll see some similar things in Pact property checking, where functions can require and can have requirements of the data that they're called with. Then they can ensure the data that they return. And we also maintain invariants at some points. Liquid Haskell is also similar in that the type you see at the top, or list, is a so-called refinement type, kind of refining a data type. And we'll see similar things in the Pact property checker. One more is Ada, which Ada/Spark. Spark is kind of a newer version of Ada, which is more targeted at proof and verification, where we see a pre and post condition here. This one is really interesting because it's been used for a lot of high-profile systems like the Boeing 777 fly-by-wire system, a lot of aerospace and rocketry. There's some similar work in Haskell. This is one of the works that's closest to our work. It was also written in Haskell and also uses the Z3 SMT solver as a backend. And this one's really cool because they're using it for rocketry as well. And the final example I have is another smart contract analysis. This one, Manticore, was built by a company called Trail of Bits, and their domain is a little bit different from ours. Theirs is, I think, a little bit harder because they analyze arbitrary solidity programs in Ethereum. So it's a bit of a more difficult domain, and they also don't have the same kind of properties that we check. But they also use Z3 as a backend. Okay, so to get into what the Pact property checker actually does, it's a static analysis tool built into Pact now. The current version of Pact has a preview version of the property checker. So it uses Microsoft's Z3 theorem prover as a backend. So what that means is we translate Pact programs and properties and invariants to Z3 and then have Z3 solve them for us. So there's a distinction which I'm going to make between schema invariants and function properties. I'll show examples of this, but in general, we've been thinking of function properties as a property that you can show of a function, and a schema invariant as kind of a refinement of data, an invariant that must be true of some schema. And I'll show an example of that. One of the design goals of this work has been that no formal verification background should be required. And I want to be clear what this is. This is not an interactive theorem prover, and this property checker is not proof that your program is correct. It's merely a means of specifying properties and invariants which the Pact property checker will check. And there are many properties which you can't specify right now. There are many invariants which you can't specify. So this is one tool among many in writing a correct smart contract. So this is the schema which we showed before. And we can add an invariant on this schema. So by default, integers are positive or negative. But we can refine this schema and say that the balance must be greater than 0. And so that was a schema invariant. And now I'll show an example of a function property. So absolute value, we all know this. One property that makes a lot of sense here is to say that the result is always greater than or equal to 0. And then we can verify this. Two more properties which are interesting in this domain, and I think interesting to functional programmers, is we can essentially say that this function is pure. We can say that it doesn't read from the table and it doesn't write to the table. And additionally, we could say that this function does not abort. So one more property I will talk about a little bit before going into a larger example. It's called mass conservation. So this is rather specific to smart contracts and money transfer. So we have this table with Alice, Bob, and Carol, and they each have a balance, and their balance is summed to 100. Now, there's going to be a transfer between Alice and Bob. So Alice transfers 10 to Bob, and now Bob has 15. But the total balance is still 100. And so what we're checking for here is this property that money is neither created nor destroyed in the execution of a contract. Is this big enough? A little bit bigger? Okay, so this is the same absolute value function that we showed before. So I just added a property that the result is always greater than 0. So it's not very interesting because right now it didn't show anything, but we can change absolute value to be buggy. And when we save it, we see that there's an orange dot. And what it shows is a little bit cryptic, but it says there's an invalidating model found. And what that means is Z3 tested all of the possible inputs to the function, and it said, and it found one, -1, where the result is not greater than or equal to 0. So it gives us an example of an input to our function which invalidates this property. So that's easy. I can just change this back to -x, and it shows that this property holds all the time. Yes?
So this actually is complete. So it means
Yeah. So
input, or it just says I haven't found any issue here.
right. So it's a little bit misleading because this looks like a little orange dot, but it's kind of a small miracle what happens behind the scenes here. We quickly translated the entire program to constraints, which we sent to Z3, and Z3 checked for every possible input to this function what the result was. So it's not that big of a deal in a small case like this because there's just one input. It's just one integer. But Z3 proved that for all possible integers that either this property was true or false. And in this case, it proved that it was false and gave us an example. But this also works if we have many inputs and much more complex control flow. Z3 will check every possible execution. Yeah?
Are there conditions where Z3 has a performance issue on certain smart contracts?
This is one of the things I'm most worried about with this work. I think you very, very easily could have performance issues, but we haven't had any performance issues yet. And in every contract which we've run, the Z3 returns more or less instantaneously. So I am worried that as we scale this up to larger, more complex contracts, then that will be an issue. I do have some ideas in mind for improving performance, but it hasn't been necessary yet.
Okay.
Yeah.
And to be clear, this generally is an undecidable problem. So there's a chance that these three.
Yes.
It's about you essentially setting a timer and giving.
Yeah, exactly.
And it's very easy to come up with properties, not in Pact, but generally to give something to these three.
Yeah, I think if you wanted to, you could very easily make this time out. But in real world contracts, which we've used, and my gut is that in almost all real world contracts, this will return very quickly.
And this three is really fast.
Yes. Yeah.
How complex is the translation from Pact with Z3 constraints?
I can show you what this translates to, if you like. Yeah, I had a feeling someone might ask this question, so I prepared this executable to show us the constraints that it sends. So there were actually two exchanges with Z3. So there's one set which is kind of on my screen now, and then another set here, which I'm highlighting. And this is the entirety of the exchange with Z3. So this is a very simple contract. So there's very little actual code being exchanged with Z3 in this case. But it's just an example, and I can show with the next example, which is a little bit larger, what the exchange looks like.
And the code that generates those constraints, is that reasonably
simple as well, or is that, how can you talk about that?
I can talk about that a little bit. Yeah, let me get to that in a bit. Any other questions? Martin?
I was just wondering if you could talk a little bit about the internal, just as before the problem gets harder, like what is the internal representation of what it considers to be like this property? Is it like encoded in some kind of transition, or like some kind of lattice, or I don't know, like there are different ways that people formulate it as a series of constraints that like a Haskell constraint that needs to be solved kind of grapically, or like what is the model that Z3 knows about for this statement? I don't know that it matters, so I want to force that answer, if anybody answer it. But I'm just kind of curious, like what it considers to be a proposition relative to like, if you think about like, it's good. It's not just like running through a bunch of guesses and figuring out like, oh, that wasn't positive. I'll move on to the next one. So like, clearly it has some kind of framework to understand what you want.
Right. Is this a question about Z3 or about the translation that we're using to Z3?
I would be curious if either, yeah, to comment on either, basically.
To me, it seems like the question is more interesting if you consider Z3, which I don't know the internals of Z3.
It has a set of skills in it. So it knows about images, knows about arrays, knows about actually, yeah. So it has just a few data types essentially that it knows about. It knows about Boolean logic. It translates the program into those theories that it knows about, and then then it reasons it.
So I have a few more properties which we can add here. So this is a property which says that it reads from the accounts table, and we see this dot pop up, and it's going to give a very silly invalidating model because basically any input would cause it to be invalidated here. But I just need to say there's no table read, and it does prove that that's correct. And then we could prove a similar thing with a table write. And we've now proven that there's no write in this module. And then one more thing. We can see if there's an abort. And our tool has a problem with abort because there's never a case in which this code aborts. And so we can prove that as well. So a lot of nice properties. These are very simple, of course, because this is just absolute value, but a lot of nice properties which you might want to be able to prove of a function like this.
Those get kind of cleaned up before they get stored. Just those properties aren't necessarily a part of the code. So I'm guessing this compiles down to some
Right.
code
So.
that's getting run on like this. Maybe it's not as similar to Ethereum.
Right, so a little bit of background on what's going on here. Everything inside this paren is a meta.
Okay.
Okay, great. And so our tool just looks for either properties or invariants, meta tags.
Similar to how types work in Haskell, like they're not actually being compiled.
Right, that's not executable.
Cool.
Yeah.
And what's the scope of these properties? So like, they can, I assume that they have scope.
Right, so we captured the scope inside a function. So the scope here, we capture x, and we capture accounts.
But like not abort, it's like a global, like I
Right.
can call a function that aborts.
There are result and abort are two kind of special names. Did that answer the question?
Yeah, so I
Okay.
can't call this, if I have a function that aborts, I can't call this, sorry, if I have I can't call a function that aborts inside of this, even though it's
Right. Right. So we can show that. I think. I think that I'm doing something wrong here, but I'm not exactly sure what while I'm on stage. But
But in theory,
Well,
this is part
but-
of the project. Right?
but in theory, yes, yeah, not just in theory. It definitely it's one of the things we focus on most. So I have one more example I want to show, which is a little bit more complex. In this case, we just want to implement balance transfer. It's the same example which we were kind of going through earlier, transferring from Alice to Bob. So the core of this function is here. And again, this is the same thing which we saw earlier, where we just subtract from the sender's account balance and add to the receiver's account balance. So the first thing I want to add is an invariant on the account schema. Because we always want account balances to be greater than or equal to 0. A negative account balance is a problem for several reasons. And when we add that invariant, we see that Z3 is complaining about the transfer function. And it's a little bit hard to see, but if thinking about this for a moment, we see that Z3 gives us a model where the integer is negative. And so looking through what would happen in that case, we would update the sender's account to be greater and the receiver's account to be smaller than it was. And so Z3 is actually complaining because we could drain the to account and even make the to account negative. So what we need to do here is if we add an enforcement that the amount is greater than 0, then we're no longer allowed to send a negative amount, and that invariant at least holds. Now I want to add one more property, and this is related to the one which we saw earlier when I spoke about mass conservation. So I'm essentially adding mass conservation here. So this just says that the delta, or the difference in that column, should be 0. In other words, mass is conserved. And when we add this property, our tool has another problem. In this case, the amount looks okay. It's 1. We should be allowed to send 1. But the thing to notice here is that both the sender and receiver accounts are the same. So thinking through what happens if the sender and receiver accounts are the same, and the amount is 1, we get to this line, and we first update, say the balance is originally 100. We first update the balance to be 99. And then on the next line, we update the balance to be 101. So we actually have created mass here by writing to the same account in 2 different places. So what we can do there, I think the simplest way to fix this is just enforce that the sender and receiver are not the same, and then the tool says that the property holds in this case, that mass is conserved.
It's crazy how quick that is.
Yeah, it's cool. Okay, so a little bit on how this works. There's this really great library in Haskell, which is the language we're using, called SBV. And SBV and Z3 together are really kind of the workhorse of this work. We translate 3 different things to SBV, which then translates them into Z3 constraints. We translate programs into SBV. And SBV, SMT-based verification. So we translate programs into constraints, we translate properties into constraints, and we translate invariants into constraints. And the way schema invariants work in a little bit more detail is whenever you read a value of a certain schema, we assert that all the invariants hold on that read. So if I read from the table where balance is greater than 0, then every time you read from it, we assert that the value you read is greater than 0. And then we check that every time you write, the same thing holds. And then we just ask Z3 to either provide an input where that's not the case. And if Z3 can't provide an input where that's not the case, then the invariant or property holds. And here's an example of more or less the Lisp that I showed you earlier. It all translates down into a large set of constraints, which Z3 generally is able to solve really quickly.
That's the SPV.
This is the Z3, the SMT lib, which SBV spits out. Okay, so there are a few limitations of this work, which I want to be clear about. So this property checker itself is not formally verified. And like we mentioned earlier, the performance on large contracts is unknown. And also, at least for now, the properties which we were able to express are somewhat limited. We'd like to make this more sophisticated, and we're looking at we're looking for inspiration from, say, Liquid Haskell and others. One big reason why properties are limited right now is because there's no way to abstract over properties. We can't define a property and give a name to a property. So one thing which would be really nice to do is define a property called pure, which says that it doesn't read from a table or write to a table or abort. And so I think this is coming very soon. This is one of the first things on our roadmap, but it's just not done yet. Yes?
The read and write checks that you put in before, they were for a specific table.
Yes.
You do it for any table?
So we have quantification. We have existential and universal quantification.
So you're saying?
So yes.
Like a splat there, or a little star, just all tables?
Yeah, you could say for all x of type table, it's not read from that table. Yeah. And lastly, a contract is only as correct as its specification. I think a great example of this is the last contract which we went through, which when we started already had a property. And then I added a property and we fixed it, but it was still not correct. We had to add another property and fix it before I felt pretty confident that it was correct. And I'm still not completely sure that it's correct. Maybe there's another property which we would like for that function to hold, which we haven't thought of yet. Okay, so a little roadmap. I already mentioned def property. We would love to build up, to be able to define properties like this, basically in the same way you define functions, build up a standard library of functions, or properties rather. And it would be really great if we changed some defaults so that by default all functions are pure. And so you have to explicitly declare that this function reads from a table, or this function writes from a table, or this function can abort. We don't support all of Pact. Parts of it are tricky. There are parts of it which we have partial support for. As an example of that, to format a string, that's very hard to do symbolically. So if your string formatting, if your format string is concrete, then we can run through and format a string for you via SBV. If your string format is not concrete, then it's much harder. So that's kind of complex, but more or less to say that there are a lot of parts of the language, even though it's a simple language, that are relatively hard to formalize. But we've gotten pretty good mileage out of the subset of it which we've formalized so far, or which we support so far. We'd like to be able to define methods as public/private. Private methods are very important for this kind of work. Again, build up a standard library. Some of the tooling, like you might have noticed, could use a little bit of work. There's a lot of improvements to make there, but I think we have a pretty good start, and it's just going to get better. And then lastly, this is a huge piece of work, but verifying the property checker. Right now, it's written in Haskell. It's a few thousand lines of code, so it's relatively small, relatively clean. But still, it would make me feel better if we were able to verify more of it. And that's it for my talk. Any questions? Yeah.
When does that execute? Does that only execute when you're like compiling and testing, or is it kind of erased and not done when you run on the blockchain?
Exactly. It's just for yeah, it's just static analysis. It doesn't run on the blockchain at all. But I believe that those properties and invariants will still be written to the blockchain, because we write exactly these contracts to the blockchain, or that's my understanding of how it will work. Yeah.
The property check has not verified. Would that include verifying SPV, or is SPV already verified?
That would include verifying SPV, but I think it would also be possible to verify just the level above SPV and include SPV in the trusted base. Like we include Z3. I think Z3 is reasonable to trust.
Yeah, because the other two is kind of as well.
Mm-hmm.
Yeah, there's a tool. I'm just curious how this would translate. You can go to Etherscan and you want to look at a verified contract that you can upload your code and it compiles it, make sure everything's good. And Ethereum uses like modifiers and things that are actually in the code, and it's not static analysis. And if you don't include that, it won't compile the same way. It's not going to check out. But if you don't include your kind of static analysis code here, it would still theoretically compile and do the same thing. You have to due diligence to paste the right stuff.
Yeah, true.
Unless you incorporated some kind of like source hash on the chain.
Yeah, well, so my understanding of how this will work is that exactly the contracts which you see are written to the chain. There's no byte code, so everything should be human readable on the blockchain. Right, it's interpreted.
What's the interface? Like, is there this API type thing? How do you? If I was on the front end and I wanted to talk to the chain.
This is, I don't know this.
Okay. Cool.
It's not a really completely off the wall question.
Okay.
Nothing that you talk about. It's you and the data force. Back when I used to be a Lisp programmer, everybody else hated the parentheses. So how are your customers dealing with parentheses?
They're happy enough using Solidity.
Oh, okay. Right, that makes sense.
Don't stick parentheses over that either.
That's a minor trade-off.
Yeah.
We were talking about the source code in the blockchain. That's an important feature. So this is kind of there's no bytecode on the blockchain. And also the source code that goes there is version. Everything is essentially inlined, and it can't be that you execute it today and a year later you execute it again and a different version of library gets loaded. This is kind of fixed. The code that is executed is there, and you can take it out and then you can just check it at any time.
Do you keep besides the code, like a hash of the interpreter? Because the interpreter can change underneath.
Well, that's the language specification. You could write your own interpreter, but in a certain sense, you could maybe even see the semantic that is generated by the property checker is essentially a form of Manticore of what kind of it. But yeah, but the language is version. So every version is supposed to have well-defined semantics, which currently I think the most formal you get is essentially looking at what the property checker generates, because SMT is standardized. So yeah, I would say it has a
Yeah.
I think in one of the slides you had you asserted a version of Pact.
Yes.
If I remember correctly, so that's not required though. You kind of float it and let it kind of.
I'm actually not sure,
Okay.
but that serves as a lower bound.
If you're just storing one major issue that blockchains face today, I don't know what Kadena's use, if it's a public chain or if it's more for consortium chains, but if they're
If you stay in this room, you'll find all about that at 3:30.
wonderful, cool. It's like the cost of storage. It's like in theory now you just write this huge contract and you just pay for it once and it's there forever, and if no one.
There's not a gas model yet.
Okay.
But in the public thing, so there are two essentially infrastructures to run this. There's a public, private blockchain, which already exists, and there's no gas model there.
Okay.
We're currently building a public blockchain, and that will have a gas model.
Have you heard of Philip Dian's work on, and maybe some of those other people
from IC3?
Cornell Tech, and they're talking a lot about the economics of storage and how just the gas model as it is right now is like, it's probably not optimal for.
Yeah, and arbitraging gas over time.
Yeah, well, there's a lot of other solutions, but like the current one is quite naive, and it probably won't last 50 years or 100 years or whatever.
Yeah.
One reason is why we don't have it yet.
Yeah,
It's
very
ongoing.
difficult.
It's ongoing work, so
Yeah.
it's definitely not. There's a lot of trade-off.
Yeah.
Inside the gas one. That's one reason why it's not yet finalized.
Yeah.
Okay, thank you.